Hello, everyone. Welcome to this lecture on the case study, queuing theory for healthcare systems. So this is the outline of this lecture. First, we're going to discuss the problem, and then we're going to develop a Jackson network model of the inpatient clinic. And this model can be used for capacity planning. That is, how much capacity should the management build in each unit to provide proper service to the patients. And then we use the two criteria. The first one is service level criterion, and the second one is the cost criterion to determine the optimal capacity. Now, the problem is very similar to the semi-Markov model case study. So Nittany Heart Center has two main parts: outpatient clinic, inpatient unit. So the outpatient clinic doctor sees the patients. In the inpatient facility, treat patients who need various surgical procedures. That is, different kinds of surgical procedures. So here there are 6 units: ER, emergency room, where the patients are brought in after suffering a heart attack. POW is a pre-operative ward where the patients are prepared for surgery. Surgical unit, that is denoted as SU, basically the operating rooms where the actual surgeries takes place. And the POU is a post-operative unit where the patients stay immediately after the surgery until they stabilize. ICU is the intensive care units where the patients stay as long as they need continuous attention and real-time monitoring. ECU is the extended care unit where the patients stay until they can be discharged. So now there are two categories of patients come to the inpatient facility. The first category is the scheduled patients arrive at POW. That is a pre-operative ward, because they schedule their appointment for the surgery. So they directly come to the pre-op ward to do the preparation. It's not brought in by emergency. The second category is emergency patient. So emergency patient, by the name, they are emergency patients. They arrive at an ER, brought in emergency, and then spend some time in the ER. It's then transferred to either pre-op ward, ICU, or extended care unit. So a patient comes to the pre-op ward, that is POW, is transferred to the surgical unit after the pre-op preparation is complete. After the surgery is done, the patient is moved to the post-operative unit. In rare cases, the patient may have to be rushed back from surgical unit to the surgical unit from POU. But most often, the patient is moved to the ICU after he or she stabilizes. Similarly, the patient can stay in the ICU for a random amount of time and then moved back to the surgical unit. Or if they are doing well, they are moved to transferred to the extended care unit. Then from the extended care unit, a patient is discharged after the doctors deem it appropriate. So now we have a new research objective. How much capacity should the management build in each unit to provide proper service to the patient? And what do we mean by proper service? That means we can use, proper means two criteria. You can use service level. That means you want to guarantee a level of service to the patients. And you don't have too many patients got to tender away from the unit or keep waiting for a long time. And the second proper definition is cost. You want to reduce the cost. So in order to do the capacity planning, we are going to develop a Jackson network model. Previously, we have a semi-Markov model, and now we are going to study the queue. So Jackson network is actually a queuing network model. So here is a network for the emergency patient. You see here, there is an arrival rate. The arrival rate is from outside. This is 0.776 per day. So in the historic data, the management find out that they have about 9.8 patients per day visit the clinic, inpatient clinic, including scheduled and emergency patient, but 19% are emergency patient. So we know that the split of the Poisson process or the thinning of the Poisson process, right? So the arrival rate for emergency patient will be 9.8 times 19%. It's about 1.862 per day. That's 0.0776 per hour. Okay, so there is 25% got discharged from ER directly, and there are 75%, that is 32% go to pre-op, 38% go to ICU, 0.5% go to extended care unit. So this is arrival rate for emergency patient per hour. Now let's assume infinite capacity. So let's first assume there are infinite capacity for each unit. That is M means this is a arrival process. This is a service time. This is infinite capacity. Okay, servers, the queue. And let's first assume this, and then let's find out the steady state distribution. This steady state distribution will help us decide upon actual capacities. The average service time, this is very similar to previous one, but now let's assume they are exponential. So this is 4.5, 2.4, 6.8, 4.4 hours, 36.7 in the ICU, and then 118 hours in the extended care units. So this is state. So this is 1. So ER is 4.5 hours. 6 is ECU. So it's 118 hours. And because we assume infinite capacity, so we have infinite servers for all the stations from 1 to 6. And the arrival from outside, this is lambda 1, that is 0.0776 per hour. And for all other units, we don't have outside arrivals, so those are 0. And we only have arrival here, then got branched to different units. And this is the mean service time. And if we calculate the rate, service rate, it's about 1 over this time. Okay. So this is the service rate. We got a mu, and we also got 0.25. That means the 0.25% got exit to the outside, discharged. So from here, because this row, if you sum them together, it doesn't equal to 1, right? But if you add them together, and also the probability to go outside, got discharged, is actually 1. For the last state, extended care units, you also have 0.88% to get discharged. Okay, so this R denotes the probability to exit directly from a particular unit. So from this unit, you can exit to the outside, discharge 25%. From this unit is 88. So for this 4th state, you cannot go exit to the outside. So their probability is 0. Okay, now we got the Jackson network established, and all the values like the server, the external arrival rate, and the service rate, and the transition matrix, and also the external exit probability to the outside is R. Now, since we got all these values, we can derive the arrival rate to a particular arrival rate, means external arrival rate and arrival rate from other units. Okay, so if we combine them together, we can get arrival rate, combine the arrival rate at a particular unit. And the equation we're going to use to calculate this is A equals to lambda 1 minus P inverse. So this is arrival rate to each unit. So in steady state, we have a mm infinity q. And for the mm infinity q, and the number of customer is approximately Poisson random variable with ai over mu I, okay, for a particular unit I. So the expected number of customers will be alpha I, that is directly lambda, if it is Poisson lambda, but now lambda is actually ai over mu I, okay? So this is the expected number of customers. Then because we have A here, we also have lambda, we also have mu. So lambda is here, P is here. With lambda and P, this is identity matrix. You can get combined arrival rate to a particular unit. Then for each unit, you have service rate and combined arrival rate. Then you can calculate expected number of customers. That's alpha I. This is the expected number of customers or patients at each unit. Here, we are counting for emergency patients. Okay, so this is the expected number of emergency patients at a particular unit. Now let's have a look at the Jackson network model for the scheduled patient. You see the scheduled patient arrive at, so here scheduled patient arrive at POW, not ER anymore. So from POW go to surgical unit and post-operative and ICU extended care unit. You see the arrival rate still the same thinning process of Poisson process, 9.8 patients per day, and then you times 0.81% they are scheduled patient. So you have 7.9380 per day, and that is 0.3308 per hour arrival. So this is arrival rate. You also have exit probability, like 91%. Okay. So similarly, we have SI, we assume mm infinity q, and we got arrival rate. So external arrival rate to all these units, they are 0. And this is the average service time. And then you can calculate the service rate. Mu is the service rate. And then this is the exit probability. This is 91%. Now, A equals to the combined arrival rate equals to lambda and identity matrix minus P. So we got the arrival rate similarly as the similar to the emergency patient. So the scheduled patient in unit I is Poisson AI over mu I. So we got a beta. Beta is actually calculated with expected number of customers or the scheduled patients. That's AI over mu I. So this is scheduled expected number of scheduled patients. So for example, the state 6 extended care units, on average, we have expected like 35.8737 patients, okay, in this unit 6. Now, in this system, we have both scheduled patients and emergency patients. The merged Poisson process is actually, then we have theta I equals to alpha I plus beta I, okay? So if you add two Poisson together, they're still Poisson. So the total number of patients is in unit I is also Poisson distributed with theta I. So we can calculate the expected number of patients in each unit, combine the scheduled and emergency patient. So we have this is the expected number of patients in each unit. So here, this is ER, and then we have, you see ER is 0.3491. It's the same as 3.491 here. Because beta 1, the scheduled patient arrive at ER is actually 0 because they directly arrive at a POW. They don't arrive at ER. So this is only the emergency patient. But for the second one, you have to include both scheduled patient and emergency patient, if we look at it, it should be 0.3307 plus 0.0596. Then what we got is 0.8534. Okay. So this is the expected number of patients at each unit. Now the knowledge is Poisson distributed with this theta I. And the knowledge on the distribution of patients in each unit help us size the unit. Because we know the number of patients is a random variable at unit I is Poisson random variable with this parameter. Okay, for unit 1, it is this theta 1. Unit 2, it is this theta 2. Now, how to plan the capacity? The first criteria is service level. We want to guarantee a certain service level. The service level is defined as the probability that a patient is blocked from entering a needed unit due to capacity restrictions. We want to make sure the patient is blocked from entering is less than 5%. But we know the number of patients in unit I in steady state is approximately Poisson random variable with theta I. This is distribution. So let's calculate probability Ni greater than this capacity. We want it to be less than 0.05. Okay, so that the probability to block the patient is less than 5%. Then based on this calculation, right, we know the distribution. We want to find the capacity that guarantee blocking rate is less than 5%. So this is what we calculate. The capacity is 1,353,21,55. So this gives us the capacity for ER, POW, pre-operative ward, surgical unit, post-operative unit, intensive care unit, and extended care unit. So the previous one is the service level criteria. Now let's have a look at the cost criteria. So the operation cost, first the DI, hourly cost of maintaining 1 unit of capacity in unit I. DI/CI is hourly cost to maintain the whole unit, because how many units we have? CI unit. Each unit will cost DI in an hour. So hourly cost to maintain the whole unit I is DI/CI. Hourly cost to serve an overflow. Overflow means the patient is actually an overflow patient. That means when the patient comes, the capacity has been reached. You have to make special arrangement so that this overflow patient can get accommodated. So the cost is much higher. It's 5 times higher. This FI is 5 times higher than the DI. Okay, that basically FI equals to 5 times DI. Now, overflow patient, overflow cost. If the coming patient is greater than the capacity, then we use Ni minus CI times Fi. This will be the overflow cost. This is actually, if Ni is less than CI, then you're under the capacity, then this is 0. You don't have overflow cost. So the expected total cost per hour for unit I is actually expectation. This is the unit I. And expectation DI, CI plus FI max Ni minus CI 0. And then let's do the expectation, because this is constant. This is constant, and this is CI. It's not a constant, but we need to determine this CI. It's a value, okay? But it's not a random variable. It's a value we want to determine. And then you have Fi, Ni. Ni is a Poisson random variable. You have theta I. And because F max is actually just the Fi max Ni CI 0 is actually equals to Fi Ni minus Fi minimum Ni CI. Because think about it, if the minimum is Ni, and then this is 0, FCI is Fni minus FCI. So it's Fm minus Ni minus Ci. So it's the same as this. We just change the notation. And the expectation of minimum NICI equals to summation n equals to 0 to Ci minus 1 probability Ni greater than n. So now we got this equation. Now let's calculate the gradient. If we add one, so in optimization, we always use gradient descent. So this is one way to calculate the gradient. We just add one to see what's the difference. So it's very easy that we add one and we will be able to derive. This will be the difference will be di minus fi probability ni greater than ci. Now, if this value, this probability is greater than di over fi, then the cost you add one is less than GICI. If it is less than DICI, then this is GICI plus one is greater than this previous cost. So when CI goes to infinity, PI greater than CI goes to zero. And we know that the overflow cost is much higher than the hourly cost under the capacity. So this is between 0 and 1. Now let's make the gradient based on the gradient, and we will be able to get optimal CI star. This is the smallest value of CI for which probability Ni greater than CI less than Di over Fi. So this cost will be minimized at this optimal capacity of unit I. Now suppose our overflow cost is 5 times. We discussed this before, 5 times the cost of regular patient in each unit. So the cost is 280 and 300, 150, 110 for each unit, okay, hourly cost. And then this theta, we got this theta before, and now we based on the probability Ni greater than Ci, it should be less than 1 over 5. Then we got this capacity. This is the optimal capacity based on the cost criterion. Okay. Now, some of you might be confusing why is this expectation equals to this, and then here I put the proof right here, and for non-negative random variable x, and this is the expectation, and this is in a probability model or theory, any book, to calculate the expectation. Then using this result, we know this minimum is actually summation. This is summation n goes to infinity, n goes to infinity. This minimum greater than. So if you separate them, if the minimum greater than n, then every one of them have to be greater than n, right? And then you can separate them because this Ci greater than n is 1, right? And this only happens when it becomes 1 only when it is less than Ci minus 1. Okay, when n is goes from 0 to Ci minus 1. If it's more than Ci, if n is less than Ci, this is 1. If n is greater than Ci, this will be 0. So that's why we get this this expectation, and this is what we got over here. Okay. So in this example, in this case study, we look at how to build the Jackson network model. So here, the Jackson network model. Okay. And then based on the Jackson network model, we do the capacity planning using 2 criteria: service level, guaranteed service level, or minimize the cost. Okay, so this is the end of this case study.